The HL portion of the lipids topic is fairly small. It just focuses on cis versus trans fatty acids. The reason why any cis-trans isomerism occurs is because there's a bond that can't rotate. Specifically here, you've got a C to C double bond that restricts rotation. That's the structural reason. Cis fatty acids are by far the more common type of fatty acid in nature. There's very limited trans fatty acid occurring in nature. Cis and trans, you should know at this point, cis means on the same side, and so this is the double bond in oleic acid, and so in one of them, the carbon chain is really what we care about in terms of cis. The carbon chain will either be coming in on one side and back out on the same side for cis, or in trans, it will come in on one side and leave on the other side, with these being H's. So this would be H, this would be H, that's cis, and in this one we've got H across from each other. Yeah. So trans versus cis. The differences in physical properties: cis fats are a little bit more bent than their trans cousins, and therefore that reduces their ability to pack together and interact with London forces. Therefore, it lowers their melting points, and they tend to be, these are the oils, these are the naturally occurring oils that we talked about in the SL videos, being unsaturated fats. Unsaturated fatty acids can be saturated via hydrogenation reactions, like we learned in the organic chemistry unit. And so essentially you're going to have C to C double bonds plus H2, and in the presence of nickel catalyst, then we can form CHCH single bonds and whatever else was attached to these carbons. So it's just like the hydrogenation reaction that you already learned. Now this can happen completely, which would make the fats completely saturated, but then there's also partial hydrogenation. And during partial hydrogenation, some of the C to C double bonds get converted to these single bonds, but some of them don't. And those unreacted C to C double bonds can often convert from cis to trans, whether it's that during the binding to the nickel catalyst, they're allowed to do that. Whatever the case, this conversion does take place. So it's during partial hydrogenation, when you don't completely saturate the unsaturated fat, that we end up with trans fats, which I think we've all, from advertising now, know are quite bad for you. There are advantages to hydrogenation, or the saturation of fats. It's more convenient for storage and packaging because you tend, when you make things more saturated, you give them better London forces, you give them higher melting points. So they tend to be semi-solids or solids, which is why they're more convenient for storage and packaging. They also break down less during the high temperature cooking, and they have longer shelf lives. And that has to do with those double bonds are more reactive, and therefore single bonds tend to be more stable. The disadvantages, however, are that trans fats, and saturated fats especially, but trans fats are double bad because they're associated with increasing the level of LDL, which is an increased risk factor for heart disease, and trans fats are associated with lowering the levels of HDL cholesterol, which is the good kind. Therefore, they kind of give you a double whammy of being bad for heart disease. They increase LDL and they lower HDL at the same time. And that is the entire HL portion, the stereoisomerism portion of lipids.